Hey everyone. So in this video, I like to talk about functions. So in our class, throughout this entire quarter, we're going to talk about a handful of different kinds of functions and some common qualities between these functions. And so I really like to introduce and define what a function is in this video. So let me begin by saying that in mathematics, we're often trying to relate two varying quantities together, and the way we usually do this are through tables, graphs, and equations. And so because these are ways of relating two quantities together, we'll usually call these things relations. And really what's in common between all of these examples here is that they're a way of describing a set of ordered pairs. And usually we'll think of these pairs as sort of input-output pairs. So let's look at a table, for example. So here, a table, it's a bunch of ordered pairs, and usually the way we visualize these ordered pairs is that really this table is just listing them out. Right, for example, this is -1 and 7, we can think of that as the ordered pair -1, 7, or similarly, 2 and 4 make up an ordered pair. And usually we think of this left column as describing our input coordinates, and this right column in our table is describing our output coordinates. Right, in other words, an input of -1 leads to an output of 7. Now when it comes to graphs, usually this way of writing out ordered pairs is through plotting them, drawing out the points. Those are the ordered pairs being described by the graph. And so if I draw this curve here, well, there are a few points on this curve, and those are the ones being described in the relation as a set of ordered pairs. And so here, for example, maybe this point here is the point -4, 1, or maybe this point here is the point 6, 6, 5. Maybe another one here is the point 5, 2. Right, so these are all points that are examples of ones being described by this relation, this graph. And so usually we think of the horizontal coordinates, the positions corresponding to the horizontal axis as our input coordinates, the first coordinate, and then our vertical axis, and the vertical position of all of our points as being described by our outputs. That's our output coordinate. Okay, so the last example I'd like to really talk about here is an equation, right? So an equation, the ordered pairs being described by an equation are the solutions to the equation. The solutions to the equation are the ordered pairs. And so in this case, one example is the ordered pair -2, the square root of 5. So I've done this one ahead of time, but we can check it out to see that if we plug in -2 for our input variable, and here I'm just going to make the choice to call x our input variable and y our output variable, then we get out we get out the square root of 5 to make our equation true. Right, so pairs of numbers that make our equation true, those are solutions, and those are the ordered pairs that are being described by an equation. Right, so maybe just to confirm this, we see that we get an output here of y when we take the square root of 9 minus -2 squared. Right, so what output do we get? We get y is equal to the square root of 9 minus, well, -2 squared is, that's +4, right? So 9 minus 4. So we do get the output of the square root of 5 for an input of -2. So here, that -2, square root of 5, that's the solution to our equation, and that's an ordered pair that's being described by that relation. And so one special kind of relationship between varying quantities is a function. So a function is a relation in which each input leads to exactly one output. Right, so if we look at a table, the table that we have above, So this table's not a function. And why is that the case? Well, we can kind of look at each input and ask, does that input go to more than one output? And so here, this -1, the input of -1, we see that it goes to +7. We see that the input of 0 goes to 1/3. And the input of 3 goes to 0. That's all fine. But when we look at the input of 2, we see that 2 goes to both -3 and +4. Right? The fact that we see this input of 2 appear twice, and we get different outputs in each case, this sort of breaks the fact, this breaks this from being a function. Right? So this is not a function. And we can kind of see that the table above because the input of 2 leads to 2 different outputs. Right? One instance, it leads to the output of -3, and another instance, it leads to the output of 4. And so if we're trying to look for a function, we want to make sure we avoid something like this. Okay, so let's take a look at another example here. So I've got a table, and I want to determine whether or not this is a function. And so if you're feeling up for it, feel free to pause the video and try this example out yourself, but otherwise we'll resume. So if we look at the previous example, we see that we get this case of the number 2 leading to 2 different outputs, right, -3 and +4, because it appeared twice in the input of our table. Right? And so the fact that we don't see any input repeat itself here in our list of ordered pairs, this means that this is a function. So yes, it is a function because, let me see how I phrased it here. So since no two ordered pairs share the same input. Right, this input of 2 leads to the output of 1. This input of 5 leads to the output of 3. 8 goes to 6, and -1 goes to 1, and there's no ambiguity there. Right, not like 2 goes to 2 different numbers. Okay, and so here, when we do have a relation that is a function, when a relation is a function, we say that the output is a function of the input. And so in this example, we usually again think of that right column as describing our output coordinates, and this left column is describing our input coordinates. In this example, we could say that m is a function of s. All right, so in this case, m is a function of s. Okay, so we were able to identify whether or not a table is a function. Right? If we see that input repeated in the table, then that tells us that the table is not a function. But how can we determine if a graph is a function? Well, we can take the same idea, right? If we can find 2 ordered pairs that share the same input, share that same x value, then that graph is not a function. Well, can you find 2 points here, 2 such points that share the same input? Well, looking at this graph, I see 2 points here, one point at -4, 1, and another point at -4, 3. Right? These are 2 points that share the same input of -4. And so what that's telling us, right, since this first coordinate is, we're kind of thinking of it as the input coordinate, this is telling us that the input of -4 leads to 2 different outputs. 3 and positive 1. And remember, a function, well, it's a relationship where every input leads to exactly one output. And that's not the case here. Right? So this is not a function. And really, this happens only when we find 2 points that lie vertical to one another. Right here, the fact that we can draw this vertical line and it crosses our graph more than once, that's telling us that there are 2 points that have the same input coordinate. And so this leads us to what we call the vertical line test. So the vertical line test tells us whether or not a graph is a function. Right? So it says that a graph is a function if and only if any vertical line I can draw, it'll cross my graph no more than once. Right, so we saw that in our previous example, we could find a vertical line that crosses our graph more than once, so the graph is not a function. Right, so here, maybe just to add on to this, really one important point to note is that if we can find one of these vertical lines that crosses the graph more than once, try to put two words together, more than once, this is not a function. Right, so here, this first graph here, actually maybe let me ask you to try this out. So which of these graphs are functions and which of these graphs aren't? Pause the video and have a moment to think about this. So for this first example, the fact that I can draw this vertical line here that touches my graph twice tells me that the graph is not a function. Right? Whatever x coordinate we see here for these 2 points, it's shared, and so that's telling us that that same x coordinate leads to 2 different outputs, the output corresponding to this y value and the output corresponding to that y value. What about this next example? Well, no matter where I draw a vertical line, it's only going to touch my graph once. And so here it does pass the vertical line test. This graph corresponds to a function. And similarly, this third one does as well. Right. Everywhere I can imagine drawing a vertical line, it touches my graph just once. And then this last example, there is a vertical line I can imagine drawing that touches my graph only once. But because there's even one vertical line that touches it more than once, this means that this is not a function. Okay. So here, let's look at equations now. So since each input for a function leads to exactly one output, we can kind of think of the input as determining the outputs for a function. And so if we have an equation and we can rewrite it so that the output is completely determined by the input, in other words, really, we can isolate that output variable and then there's no opportunity for multiple outputs, and we can view this equation as a function. So let's look at the equation below. Let's show that y is a function of x. And again, this is saying that here we're trying to look at y as an output variable and x as an input variable. Just by the phrasing, right? When we say one quantity is a function of the other, the first one is talking about the output, the second one is talking about the input. Okay, so here, let me ask you to pause this video and see if you could work this out yourself, and we'll go over it together afterwards. So the idea here is that we want to isolate this output variable and see if that output is completely determined by our input. And so our output variable, to isolate it, we ought to subtract 8 from both sides to get 4x minus 8 is equal to negative 2y. And then again, to get that output variable further alone, we want to divide both sides of the equation by 2. And again, this equation, it's saying that these two quantities, they ought to be the same. And so if I'm going to divide both sides by 2, I'm going to divide the entire left side, by -2, and the entire right side by -2. All right, so some mistakes that I see frequently when it comes to these kinds of problems is students forget to divide both of these terms by -2, right? This dividing this left side by -2 amounts to dividing every term on the left side by -2. It's kind of like distributing it. And so here this comes out to be -2x plus 4, because that -2 is dividing both terms. And then on the right side, well, we just have y. And so this does it, right? We've got y completely isolated, and whatever input we plug in for x, we multiply that by -2, add 4, and that's going to be the output. It's completely determined. There's no opportunity for us to decide a second output possible for that input. And so here, this is indeed a function. Y is a function of x. Now let's take a look at one more example. I want to determine whether or not y is a function of x. For this equation, x squared plus y squared is equal to 16. And if you're feeling up for it, please give it a try, but we'll talk about it together in a moment. And so here, if I want to determine whether or not y is a function of x, I want to try and isolate that y variable. And so to do that, well, here we would need to first begin by subtracting x squared from both sides, right? So here that gives us y squared is equal to 16 minus x squared. And then, we don't want y squared, we want just y. And so we can take the square root of both sides. And when you're trying to solve an equation, you're sort of applying square roots to both sides of the equation, you ought to take plus or minus the square root. Right, the idea here is that, if maybe just a brief aside, let's say I wanted to solve the equation x squared is equal to 9. Well, if I wanted to apply the square root to both sides to get all of the solutions to that equation, I would take plus or minus the square root of 9 to get x is equal to plus or minus 3, right? Positive 3 squared gives me 9. Negative 3, when I square that also gives me 9. And so I really needed this plus or minus when I took the square root of both sides to find the solutions, all the solutions to this equation. And so when we do the same thing here, when we apply the square roots to both sides, we really need to take plus or minus. Okay, so notice that here we actually, because of this plus or minus, we actually end up with 2 outputs for each input. Oops, I accidentally erased that minus sign. Right, for example, if we let x equal 3, so this leads to 2 different inputs, or 2 different outputs. Right, let's check that. So here y is equal to plus or minus the square root of 16 minus, well, I'm letting x be 3, minus 3 squared. This is y is equal to plus or minus the square root of 16 minus 9. In other words, y is equal to plus or minus the square root of 7. So really this input of 3, right, it leads to one output of positive square root of 7, but it also leads to another output of negative square root of 7. And so really this is telling us that our relation, our equation here, it's not a function.